Artificial intelligence writes essays, paints pictures from a sentence, and steers cars down a highway, and almost none of it was explicitly programmed. Nobody wrote the rules. Instead, these systems learned from mountains of examples. But what does it actually mean for a machine to learn? Strip away every bit of the hype, and what's left is one beautiful, almost mechanical idea. The whole thing, from a tiny network to the largest models on Earth, comes down to rolling downhill. Start with what a neural network really is. Underneath, it is just an enormous mathematical function. Numbers go in, the pixels of an image, the words of a sentence, and numbers come out, a label, or the next word to say. And in between sit millions, sometimes billions, of adjustable little knobs called weights. Those weights are everything. Change them and you completely change what the network does. They are the network's entire personality. So, learning is nothing more than finding good values for all of those knobs. But you cannot possibly just guess them. There are millions, and they all interact in tangled, invisible ways. So, the network is not going to guess. It is going to discover them by feeling its way there step by careful step. And to feel its way, it first needs a way to know when it's doing badly. That's the first ingredient, a measure of wrongness. We feed the network an example whose correct answer we already know. We compare its guess against the truth, and we boil the difference down to a single number called the loss. The loss is small when the guess is good, and large when the guess is bad. And just like that, the entire goal of learning collapses into one short sentence: make the loss as small as you possibly can. Now, picture it like this. Every possible setting of all the knobs is a single point on a vast landscape, and the loss is the height of the ground at that point. Good settings sit deep down in valleys. Bad settings stand high on peaks. Learning, then, is just a search for the lowest valley in that landscape. With one catch, the landscape has a million dimensions, and we can only ever feel the ground directly beneath our feet. But that turns out to be enough. Stand anywhere on a hillside in thick fog, blind, and you can still feel which way the ground slopes downward. So you take one small step in that direction. You feel the ground again. You step again. Keep doing that, and you will tumble your way down to a valley floor. That, almost exactly, is the algorithm that trains every neural network in the world. It is called gradient descent. The word gradient is simply the mathematician's name for that slope, the direction in which the loss rises most steeply. So, to go down, you just step in the exact opposite direction of the gradient. Measure the slope. Step against it. Measure again. Repeat. That single loop running over and over is the entire engine of learning. Everything else is detail. So let's watch it work on the smallest possible example. Imagine a network with just one knob called W, and suppose its loss is the quantity W minus 3 squared. We can see the lowest point is where W equals 3, but let's pretend the network is blind to that. The slope of this loss, its derivative, works out to 2 times the quantity W minus 3. Start the knob at W equals 0. Plug it in. The slope is 2 times negative 3, which is negative 6. A negative slope means downhill lies toward larger W. So we take a step. The rule is new W equals old W minus a small fraction of the slope. Use a fraction of, say, 0.1. New W becomes 0 minus 0.1 times negative 6, which is 0.6. Now repeat from there. The slope shrinks, the steps shrink, and W creeps upward, 0.6, then 1 and change, then closer and closer to 3, settling right into the bottom of the valley. The knob found its best value entirely on its own, just by following the slope down. That little step fraction has a name of its own, the learning rate, and it matters enormously. Set it too small, and learning crawls along for an eternity, inching toward the valley. Set it too large, and every step overshoots the bottom, bouncing back and forth across the valley, or even flying off to infinity and blowing up entirely. Choosing it well is genuinely half the art of training a network. Now blow this idea all the way up. A real network doesn't have one knob. It has millions of them. So the landscape is no longer a simple curve. It's a rolling surface in a space with millions of dimensions, impossible to picture. But the idea does not change in the slightest. We work out the slope along every one of those millions of directions at once, bundle them all into one giant arrow, the gradient, and nudge the entire network a single hair downhill. But here is the genuinely hard part. How on earth do you compute the slope for a million knobs efficiently when the loss depends on every one of them, all tangled together through layer after layer after layer? Do it the naive way, one knob at a time, and training a serious network would take longer than the age of the universe. The breakthrough that makes the whole field possible is an algorithm called backpropagation. To understand it, first follow the numbers forward. An input enters the network and flows through its layers. At each layer, every neuron takes a weighted sum of all the numbers feeding into it, and then passes that sum through a simple squashing function. Layer by layer, the signal is reshaped and transformed, until the final layer produces the network's answer, and we measure the loss. This is the forward pass. Backpropagation runs that entire process in reverse. Starting from the loss, all the way at the output, it walks backward through the network, layer by layer, and at every step it asks one question: how much did each weight right here contribute to the final error? It is a vast, beautifully organized exercise in assigning blame, and it leans entirely on a single rule from calculus, the chain rule. The chain rule is really just this. If a tiny nudge to an early knob changes the next layer a little, which changes the layer after that, which finally shifts the output, then the knob's total effect on the loss is simply all of those little effects multiplied together, straight along the chain. Backpropagation computes these ripple effects starting from the output and moving backward, cleverly reusing each result it finds, so the slope for every weight in the entire network drops out in a single backward sweep. So one complete step of learning is really just 3 moves. Forward, run an example through the network and make a prediction. Backward, backpropagate the error to find the slope for every single knob. And update, nudge every weight a tiny bit in its own downhill direction. Predict, assign blame, nudge. Predict, blame, nudge. That short, relentless cycle is the whole of how a neural network learns. Then you simply do it again, and again, millions of times across millions of examples, each pass shaving the loss down by another sliver. Slowly, the knobs stop thrashing and start to settle. The predictions sharpen. And a network that began as nothing but random noise gradually becomes something that can recognize a face in a crowd or finish your sentence before you do. One small detail is what makes the whole thing powerful, that little squashing function sitting at every neuron. Without it, stacking layer upon layer would be pointless, because a stack of straight lines is still just a straight line, no matter how tall. That nonlinearity is exactly what lets a deep network bend and fold its landscape enough to capture genuinely intricate patterns instead of only drawing straight boundaries. In practice, there's one more shortcut. You don't measure the slope using all of your data at every step. That would be agonizingly slow. Instead, you grab a small random handful of examples called a mini-batch and estimate the slope from just those. It's a noisy estimate, a slightly drunken stagger downhill rather than a perfectly straight march. But it is dramatically faster, and the noise even helps the network shake itself loose from bad spots. This is stochastic gradient descent. You might reasonably fear that a blind, million-dimensional fog walk would get hopelessly stuck. Astonishingly, it usually doesn't. In very high dimensions, true dead-end valleys, where every direction leads up, turn out to be incredibly rare. Far more common are saddle points, places that look stuck but always have at least one direction still sloping down. So there is almost always a way onward, and the simple act of going downhill keeps on working. And what do all those settled weights actually turn into? Feature detectors. In a network that looks at images, the earliest layers learn to fire on simple things, edges, and patches of color. The next layers respond to shapes and textures. Deeper still, to eyes and wheels and whole faces. Nobody hand-designed any of those detectors. They emerged entirely on their own, purely from the constant pressure to push the loss a little bit lower. And here's the quiet shock at the end of it. This single loop, predict, measure the error, roll downhill, repeat, is essentially how all of it learns. The model finishing your text. The one painting a picture from a sentence. The one steering a car through traffic. Wildly different shapes, wildly different data, and an almost unimaginable scale. But underneath every one of them is the very same patient descent down an error landscape. Step back, and it is genuinely staggering. Nobody writes the rules for recognizing a cat, or for speaking fluently, or for driving. We do something far stranger and far simpler. We just define precisely what being wrong means, and then we let the network feel its own way downhill, one tiny correction at a time, until wrong slowly, grindingly becomes right. Something like intelligence, falling out of nothing more than slope. So that is what it truly means for a machine to learn. A vast landscape of error, a fog far too thick to see through, and one simple, relentless rule: feel the slope, take a step downhill, and repeat. Millions upon millions of times over. It was never magic, and it was never a mystery. It is just a very long, very patient walk all the way down to the bottom of a hill.